Good afternoon, everyone. I'm Kshitij. Thanks for joining, and I'm actually here in Cambridge. I'm on Zoom, but uh, hopefully I'll see some of you around while I'm here. Uh, so yeah, today I'm going to talk about a recent work which appeared at CVPR, which is like a vision conference on training diffusion models with privacy guarantees. This is joint work with my lovely collaborators at Hong Kong University, NJIT, and UNC Chapel Hill. Okay, I'll start away and feel free to ask me questions and interrupt me in between. I think I've tried to keep it within an hour, so there should be ample time for questions. Okay, so I'll begin with like a general anxiety that we might have heard, or maybe not, which is that it appears that the large data hungry models, especially the language models that we are training, are running out of data. And the data that they have been currently trained on, I don't know if you saw the news yesterday, but Anthropic paid out about 1.4 billion in a quote in basically two authors of the books they didn't get permissions from before actually training on their books. And about a dozen newspapers are still with like pending court cases against OpenAI and Anthropic. So it's not even clear whether the current models would actually be able to win these cases and stay online. And this is true for language models, but there's almost a paradox that you see when you look at electronic health record data, which is that a lot of electronic health record data is produced every day, but according to a World Economic Forum estimate, 97% of it does not get used. And that's surprising. A lot of people tend to ascribe this to strong privacy protections and strong compliances that this data has to follow. And I'll give a US specific example, but I'm pretty sure the story is similar here. In 1996, when HIPAA was passed in USA, there was almost an overcorrection in medical agencies in terms of what they should be sharing, what they should not be sharing. And there was almost a conservative attitude towards not sharing any type of data because that might lead to lawsuits or additional costs associated with managing compliance, etc. And to actually correct for that overcorrection, in 2016, the government had to pass another bill where they had to make it clear that the goal of HIPAA was actually to increase the interoperability of electronic health record data and to avoid any sort of information blocking and to actually enable the use of electronic health record data for medical clinical research. And while I'm talking about like as a running example, medical data today, this is true in general. Like as a society, we are producing a lot of data. This is a graphic just to elucidate how different modalities we interact with, like a fitness tracker, perhaps a car, other devices that share our location, like a laptop or like a mobile phone. All of these produce a lot of data. All the tweets that you do, TikToks, Instagram, all of this is data which contains rich personalized information, which can tell us a lot about individuals. And largely, this data has not been tapped into. Even the large language models used by companies like Meta cannot directly use this type of data. And as such, this presents a huge opportunity, both in medicine as well as in other domains, to train next generation of AI models. So going away from platitudes, I'll go with like a running example. Imagine you have multiple hospitals and each hospital has some chest X-ray images. So chest X-ray images would be our running example for medical imaging data sets. Uh, for now, assume each hospital has like a finite data set which it draws from the same distribution, calligraphic D. And each hospital wants to solve some task using this data set. So the tasks could actually be different across the hospitals, like the different loss functions denote expected losses for different tasks. And what could these tasks be for X-rays? You could want to do disease classification. You could want to localize infected regions using bounded box. You could try to predict how the severity of the disease is changing. You could maybe use it for something else, like create a policy for allocating resources. Or in general, you could try to learn some general purpose embeddings, which you can use for many things. But as such, there could be many different tasks you could want to solve with chest X-ray images. And one naive way to solve this problem is to basically concatenate all the data together and just solve empirical risk minimization on each client with their respective losses. And assuming nice things about these loss function, uniform concentration will give you some guarantee over the population objective that you care about. But of course, the con of this protocol is that this requires training M, if not more, different models for each of these tasks. And if we don't have a reliable way to predict what tasks we might need to do in the future, then we might need to repeat the process again. Okay, and as you might have noticed, this is an overly simplified setting because in practice, you probably wouldn't have the same sampling distribution on each hospital, nor like the same sample size. So there's data heterogeneity at the source, and the tasks that each hospitals have might also rely on different data distribution. So I might want to solve a population, optimize a population loss where the distribution changes across the clients. And this is in these, both of these types of heterogeneities are real. We see them in practice, which you guys might know much better than I do. So this not only requires training M different models, but we need to adjust for data heterogeneity both at the source and the target distribution for each of these clients. We might need to correct for selection biases, or maybe a hospital only cares about a certain population. So the adjustment itself might change across the hospitals. And one natural solution to deal with this is instead of trying to solve each optimization or learning problem individually, we could try to come up with a way to generate good, high quality synthetic data for all the clients. And once they have access to such synthetic data, in future, they could just train a downstream model on that synthetic data without needing to collaborate across the hospitals, as long as everyone has, let's say, API access to some synthetic data generator. So how would you imagine this would happen? You again have these hospitals and you just combine their data set, pool it together. And one natural way to generate synthetic data these days, the best models that would work for images these days, would be diffusion models. So what do diffusion models do? This is like diffusion models in one image, but we'll go over some of the math later as well. They basically do this process called forward diffusion, which progressively noises each of these clean images by adding Gaussian noise to it until you ultimately end up with pure white noise. And although I'm using the example of Gaussian noise, there's a way to do this with other distributions. The goal is that ultimately you want some easy to sample from distribution. In this case, that's like a Gaussian distribution. And where does learning come in? Machine learning comes in because now you train a neural network to denoise this Gaussian image and recreate a clean image. And you do this for every image, and you actually also pass like a time embedding to the neural network, which tells it how to denoise at a particular time step. So as we'll see later, the forward diffusion happens over multiple time steps. So you can actually ask to denoise at different time steps as well. Once you have somehow trained this network, the way generation works in the future is you generate a random seed, you pass it through the model, it progressively denoises the image and results in a synthetic image, which hopefully looks like the combined dataset. And if you've used any AI model, any LLM to actually generate images, like just asked it to generate an illustration or maybe asked it to edit an image of yours, it's using a diffusion model in the backend, some version of a diffusion model in the backend. Maybe it's a diffusion language model, which can also accommodate language input, but for the generation of the image itself, it's using a diffusion model. Of course, this naive method of just applying throwing diffusion model to this combined data set has a big problem, which is that it does not have any formal privacy guarantee. And this global model can be attacked to reveal sensitive information. And note that a naive de-anonymization or just using federated learning to train this diffusion model wouldn't solve the issue, because as long as the model is publicly available, it could very well have memorized some of the data which might be very sensitive for these patients. And this is not just a concern, it's a natural, very grounded, informed concern actually. So this paper for 2023 tried to attack diffusion models to try to understand what do they tend to memorize, or whether if they even memorize. And diffusion models, unfortunately, are very prone to strong reconstruction attacks. So here you see an image of a US representative, Anne Graham Lotz, and her image appears in the training set, and through an attack, a white box attack that the authors in this paper describe, they were able to actually generate the very same image that occurred in the training set. So it's not the case that they were able to generate another picture of her. They were able to generate the very same image that existed in the training set, which you can, I don't think I need to convince you, is a big privacy violation. And they, of course, repeated this exercise across multiple data sets. And this is not just unique to reconstruction attacks. If you wanted to do something like a membership inference attack, where you wanted to infer whether a particular patient was in the training data used to train this diffusion model or not, they showed very successful membership inference attacks as well. So on the left, this is like an ROC curve. The dashed line is y equals to x. So as we change the false positive rates, if the true positive rates are on the upper left, then that's a super successful attack. So the blue and orange were the new attacks that they devised. The green attack is a usual likelihood ratio based threshold attack, which is common in this literature. And even that had a reasonable privacy leakage. And not only that, they actually showed that FID score, which is a measure of fidelity of the images, or you could say the quality of the images the diffusion model generates. So the lower the FID score, the better usually the quality is. And the better the quality of the image, they saw that the attackability of that image actually increased. So if you could generate image for a particular prompt very, very well, then it was much more likely to be able to run a membership inference attack on that image. All of this is very concerning and suggests that we cannot hope to naively apply diffusion models to medical data, which is sensitive. So before I tell you what we might do, let me go over like one slide and the next slide over how diffusion models are actually trained. And this is based on something called DDPM, which is based on this 2020 paper from Ho et al. And let me describe what the algorithm is. So you sample a clean image from your data set. So this is the distribution where you want to sample from. And when I say a distribution, you can think of a distribution as a distribution over all cats or dogs. And I might have a finite sample from the distribution. I want to generate novel examples from that distribution. So you sample a clean image from a data set. And then, as I said before, for capital T time steps, you progressively noise it with Gaussian noise. Naturally, okay, and because you do this recursively, you can unroll the recursion and write everything in terms of the original image and some Gaussian noise. For a sufficiently large T, and I didn't write this here, unfortunately, but if you control the variance of the multivariate Gaussian, for T large enough relative to sigma square, you can actually show that the final iterate approaches the Gaussian in whatever choice of divergence you want to pick, like W2, KL, anything. It'll approach a Gaussian. That's not surprising. What's surprising is that when you actually look at a reverse time step somewhere in between this chain, when you look at the probability distribution of xt minus 1 conditioned on xt, then it turns out that it's approximately Gaussian. That is very surprising and should not be obvious. It is indeed true that if you also conditioned on x naught, you would hope to see something which is Gaussian. But without conditioning on x naught, a single denoising step also looks Gaussian. And of course, you need assumptions to prove this statement. You need to make assumptions on the original data distribution, have bounded moments and all such. You also need to control the scale. Like generally, this statement becomes more true when capital T is very large. And there's a lot of math from sampling, SD, literature, and optimization that goes into proving statements like this. But this key observation is what allows diffusion models to work, because if a single denoising step is indeed a Gaussian, then I could just try to estimate the mean of this Gaussian, set its covariance to identity, not try to model it, although some works also try to model that. And I could just use a neural network to try to approximate the mean of this Gaussian at every time step. And that's the key idea. That's removing all the bells and whistles. This is the simplest idea behind what a diffusion model does. It models a single denoising step in this diffusion process as essentially like a Gaussian, and then it tries to mean estimate for that Gaussian. And if we put it in a pseudocode, essentially the way you train this model now is that at each time step in line 2, you sample some data point, and then you also sample some time. So you have to uniformly sample time because you want to be able to denoise at every intermediate time step, not only at particular time steps. And after sampling the time, you essentially look at the prediction error for the noise at any time step. So you are essentially trying to predict the noise that was added at time t to go to image at xt plus 1. And you can think of this as either predicting the noise or predicting xt minus 1 from xt. Both are equivalent of up to affine transformations. And you take a gradient of this loss function. This is like a mean estimation loss. You take a gradient of this, and you do this often enough, and then you have a trained denoiser z theta, which you can then use to start from a random Gaussian seed and produce a clean image. So this is the key idea behind diffusion models, but of course, there's no formal privacy guarantee here. One way you could think of adding privacy here is, if you note, line 6 is the only step where essentially x naught appears in the pipeline, because this generates the loss function, and the loss function is then converted to a gradient, and then that passes information about that data point. So a canonical thing you could try is you could actually clip the gradient. By clipping, I mean just L2 clipping, or like making sure that its norm is not bigger than something else which is pre-specified, and you could try to add Gaussian noise to it. This is called the Gaussian mechanism, and it turns out that if you clip with an appropriate magnitude and add noise proportional to some calibrated variance level, then the final released model, which is this final z theta model, it satisfies differential privacy. And this is called the Gaussian mechanism. Let me now define what differential privacy is, because although some of you might know about it, I want to make sure we use the same notation, because we'll have some formal guarantees later as well. So differential privacy is defined using the concept of neighboring data sets. So you have two finite data sets, D and D prime, that only differ at a single point I. So D has xi, D prime has xi prime. We say D is a neighboring data set of D prime and vice versa. And any randomized algorithm, in our case, this stochastic optimization algorithm would be the randomized algorithm in question from the previous slide. So any randomized algorithm satisfies epsilon delta differential privacy if for all neighboring data sets D and D prime and any measurable event O, which could occur, you want to guarantee that the probability of MD in O is at most e to the epsilon probability of MD prime in O plus delta. And of course, you can switch D and D prime. So essentially, this tells you how close the outputs from these mechanisms are under these neighboring distributions. And essentially what DP is saying is that if you change just one person in your data set, then it cannot change by much the probability of any observable event for small enough epsilon and delta. So imagine delta is 0, epsilon is 0, and then essentially there's no way to distinguish between these events. And this fundamentally limits an adversary's ability to infer members in a data set. There's a neat, maybe one-page proof to show how you can bound your true positives and false negative rates for membership inference attacks in terms of the epsilon delta parameters of differential privacy. I'll not do that, but that derivation is standard. In particular, note that this is a statistical guarantee, and even if you throw infinite computation, you wouldn't be able to actually demarcate between these two data sets. So there's also like a hypothesis testing view of differential privacy. Differential privacy definition is now folklore, is due to Dwork, McSherry, Nissim, and Smith around circa like 2003. And to tell you a bit more, the mechanism that we just saw on the slide was like Gaussian mechanism. And Gaussian mechanism relies on something called L2 sensitivity. So if I'm trying to actually look at a vector valued function f, its L2 sensitivity is the max it can differ across two neighboring data sets in L2 norm. And a mechanism must add noise relative to this sensitivity in order to protect the privacy of individuals in the sense of differential privacy. And in particular, Gaussian mechanism needs to add noise, which scales like this. So it's actually proportional to sensitivity, L2 sensitivity over epsilon, and depends on this log 1 over delta as well. And in general, Gaussian mechanism with this amount of calibrated noise, which depends on the sensitivity, of course, gives you epsilon delta central dp, which was the guarantee I showed you on the previous slide. So you could ask, okay, so we have a very clear algorithm. It's widely adopted. Why can't we just use it to perhaps train a diffusion model? And let's try to see how that would look like. So again, going back to our example, there are these multiple hospitals, each with these images. There's a model theta that corresponds to a neural network that we want to become the denoiser eventually. Each client samples a fresh point from its distribution. And then they compute a stochastic gradient with respect to the loss that corresponds to the diffusion model. And of course, as I showed you before, the diffusion model also samples a time step for each client. So each client calculates the loss for a particular time step, calculates the gradient, stochastic gradient, and then clips it, and then communicates it to the server. And then the server aggregates it, aggregates these clipped gradients, and then adds Gaussian noise on top. And how do we update? We basically update with this aggregated gradient. And assuming we do this again and again, you'll eventually end up with a model theta final. And you can actually show that the Gaussian mechanism also has something called advanced composition, which means that over several iterations of this optimization algorithm, note that you adaptively apply this Gaussian mechanism because the model at one time step depends on the model at the previous time steps and so on. But this advanced composition guarantee allows you to give like a closed form for how big sigma needs to be as a function of the clipping threshold as well as the total training horizon over which you do your optimization. So I'll not go into that detail, but there is a way to actually get an end-to-end differential privacy guarantee by using this algorithm that I'm describing in one slide. And this algorithm is uh, appropriately called DPSGD, differentially private SGD. It's due to Abadi et al., I think around 2005. Sorry, I missed that reference. So we could just use this algorithm, and indeed, we use these type of algorithms in many settings. So if you're using an iPhone, probably the emojis that you use in your phone have used DPSGD because people on the back end want to estimate some statistics about your emoji usage to actually suggest you new emojis. So at least at some point, Apple used to even release their differential privacy numbers for different softwares that they actually used and which relied on training on user data. The US Census uses differential privacy, not exactly DPSGD. They use it for histogram, so they use other mechanisms. But DPSGD is arguably the most popular differentially private algorithm for machine learning models. One thing you might have noted is that individuals are actually sending clean but clipped data to the server. And actually, they don't even need to clip it because the server could have clipped the stochastic gradient. So they really need to trust the server in order to do this. The privacy guarantee essentially constrains the public output. So everything the server outputs, which is this stochastic gradient, which has Gaussian noise on top of it, it does not constrain what the server can itself see internally. So if the server is not trusted, then all of this doesn't work. And note that we need to be super careful about what is the protected unit. Is it like a single chest X-ray image? Is it an entire hospital? Is it all the chest X-ray images that correspond to a single patient? All of them can be used to define different notions of neighboring datasets. But you could ask, okay, so this 2023 paper showed these negative memorization results for diffusion models. Why did they not try DPSGD? I just told you DPSGD has been around since 2005. It turns out that they did. It was just extremely hard to apply DPSGD. So even with extremely large numbers of epsilon, so epsilon was the parameter that gave us our DP guarantee. Even with epsilons around 50, which is very large, and you might say that's a mathematically vacuous guarantee if I give you that one, they were not able to train the diffusion model. And not just noising, even if they just clipped their gradients, no noising, just clipping of the gradients, which in itself can be viewed as like a privacy mechanism, they were still not able to train it successfully. And as such, they said DPSGD was not successful even on data sets of size CIFAR 10, which is not a big data set. It's a modest, I would say small academic vision benchmark these days. There has been some progress in being able to DP train these models in the last 2 years, but I'll come towards it towards the end. All right, so let me now tell you what we propose to do. So we are not going to actually use DPSGD. We are going to use something which should hopefully appear a bit simpler. And after I'm done with this slide, this should appear almost trivial. And you might think, okay, why wasn't this the first obvious thing to do? So we have these clean chest X-ray images on each client. And now instead of training like a central large diffusion model or a central large denoiser, because the diffusion model is essentially like a denoiser, you train a small one on each hospital. So you train a small one on each hospital, but you don't train it to map to Gaussian noise. Instead, you train it to map to partially noised chest X-ray images. So you can view a diffusion map as essentially like a transportation map between two probability distributions. And the forward diffusion process is something you can mathematically state, like you just need to add several steps of Gaussian noise. The reverse process is what is the transportation map. And previously we were using the multivariate Gaussian as the destination distribution because it was easy to sample from, but we might as well choose some other distribution, like in this case, some noisy chest X-ray images. Okay, then we'll aggregate all of these noisy chest X-ray images together and then repeat the process. Then we'll train like a public model that actually does forward diffusion and then trains like a large and potentially public model to do the reverse diffusion. And at generation, how do we generate? So we first take a random seed, get something out of the public model, pass that on to the small diffusion model on the client, and voila, we have like a clean image on the client. And that allows us to generate like a pipeline to take a random seed from an easy to sample from distribution, which is Gaussian noise, and get a clean image. So each hospital needs like a private small diffusion model and access, like an API access to a large public diffusion model. And the great thing is that this approach can be shown to satisfy differential privacy for each image in each hospital. So what this means is the notion of our neighboring data sets would be the following. We take all the images across all the hospitals, make a big data set. We look at a neighboring data set of that big data set, and that would be our differential privacy guarantee. This is mostly it. And there's one more small thing we really need to do, which is somehow control the sensitivity, because as I told you before, the Gaussian mechanism needs to know what's the sensitivity of each image to the output of the mechanism. So here, first of all, note that each client, let's say it performs T naught steps of forward diffusion. Previously, it was capital T, so we are using T naught to be much smaller than capital T. So you don't fully noise the image all the way to Gaussian noise, you partially noise it. And this, of course, is big time step T. So somewhere in between, we need to control like the sensitivity. And the way we do that is we actually clip these images that go into the training of the global model. You might ask, okay, we can do that. We can clip the images. But if we clip the images, wouldn't we also generate clipped images? Indeed, we would. So if we clip the images which were used in training this public model, then indeed we will generate clipped images that come out of this model. So I also need to tell you how do we end up giving these clipped images to the private models in order to generate the clean image. And we tried several things to do that, but the simplest thing that ended up working was actually augmenting our original data sets with clipped variants of the images. So in vision tasks, it's very common to do data augmentation, things like rotating your image randomly or cropping it randomly in order to avoid what is called learning spurious correlations from the images. Clipping can be viewed as a data augmentation as well. So the way we do it is we actually do conditional generation. So we might have classes like chest X-ray with tumor, chest X-ray without tumor. We add two more classes, chest X-ray with tumor without clipping or with clipping, and chest X-ray with tumor with clipping or without clipping. And on the client, that allows us to generate both clipped and unclipped images. But when we aggregate the dataset, we only pass the clipped images for training the public model. And that ensures that the sensitivity of each of these images to the training of the public model is actually bounded. And nice. Now, so once this public model actually gives us these clipped images, we can take those and still we are able to generate clean images from the client. You might say this this last step looks a little fishy still, because the aggregate distributions on the clients would include both clipped and unclipped images, but the aggregate distribution that the public model sees only consists of clipped images. But I claim that if you squint close enough, then after adding noise, there's not much of a difference. And to give you a visual proof, these are actually the outputs of the shared model after it has been trained. And actually clipping it or not clipping it doesn't change it visually too much. So the fact that these images are partially noised makes it easier for us to ignore the fact that they are clipped, and actually the model only ever sees clipped images. So this is more of an empirical fact, but this is actually crucial to get our formal privacy guarantee. Uh, Before I go and give you our main theorem, which is the privacy guarantee, you should notice that this form of protection that we saw in this algorithm seems to be strictly stronger than central differential privacy, because the server actually never even sees stochastic gradients coming from a client. It only sees noisy images. So it sees images like the ones you see on the slide. And by the way, what's the original data set? This is MNIST data set. So colored MNIST data set. So you have digits from 0 to 9, but clearly you don't see digits from 0 to 9 here. So this feels a stronger notion of privacy because I don't even need the server to see something like a stochastic gradient. And it is indeed a stronger notion of privacy. It's called local differential privacy. So local differential privacy, its definition is similar in the sense that it's also like an indistinguishability guarantee, like the central DP guarantee, but it actually looks at different notions of neighboring data sets. So instead of looking at D and D prime, it basically looks at an algorithm R, and it makes the following two things indistinguishable: the output of R on X and on X prime, where X and X prime are any possible inputs. In our cases, X and X prime could be any chest X-ray images. So the first time we look at it, this feels very weird because this feels the opposite of what machine learning or statistical learning guarantee should give you. It tells you that it doesn't matter whether you give the algorithm X or X prime, its outputs are going to be indistinguishable. But again, note that the whole point of differential privacy is actually to be able to learn things about the population without learning too much about a single individual. So this is the guarantee. And again, small epsilon means like a stronger privacy guarantee like before. But as opposed to central differential privacy, here we need to make no assumption about the central server or aggregator. We don't need to assume it's actually trusted. And as such, it's stronger than central differential privacy. If you have epsilon delta local differential privacy, then you can get epsilon and delta central differential privacy. And this is like one slide to summarize it all. The central mechanism that we saw before, it actually first looks, if f is the function whose output I want to privatize, it directly adds noise to the output, and then it relies on this L2 sensitivity, but it needs like a trusted curator. The local Gaussian mechanism, instead of operating at the level of the data sets, it operates at a single data point. So in our DPSGD example, instead of clipping the stochastic gradients and sending it to the server, I'll clip the stochastic gradients, add noise, and then send it to the server. And you can imagine that when the server averages things, the noise still works out because this is IID Gaussian noise, so it averages out across the clients. And you'll still see signal which you can use to train your machine learning model. And again, this is like a formal way to define what we called clipping before. So for any vector x, this is our clipping operation. And clipping ensures that the L2 norm is bounded. And as such, it implies that the sensitivity for any 2 points is also bounded because the points are essentially in a bounded domain. And this is what the Gaussian mechanism does. And this is how it bounds the sensitivity. So this is our final theoretical guarantee for any data set of data sets actually across all these M clients. If we choose our diffusion depth as T naught, so T naught was essentially the number of time steps until I do forward diffusion on each client, and total number of steps as capital T. and I use some noise schedule. So if you remember, the noise schedule is what told me how much noise I'm adding at each time step on during the forward diffusion. We also fix some clipping parameter big C. Then for each image in this aggregate dataset, we have the local DP guarantee, which depends on C, sigma, delta, and yeah, this is our local DP guarantee. The first thing in the parenthesis is the practical epsilon. The delta is just delta. And the sigma that we really need to use is going to be dependent on the noise schedule itself. And I know this is a bit too abstract to actually make sense of. So to give you an example, if you had 1,000 steps of forward diffusion, a linear noise schedule, and a clipping parameter at strength 10, and you chose T naught equals to 690, then that would give you something like 10 comma 10 to the power minus 5 LDP guarantee. So for the rest of the talk, for some of the empirical results that I'll show you later, we'll actually restrict to this level of privacy, epsilon equals to 10, delta equals to 10 to the power minus 5. Usually the way to think of it is delta should be smaller than 1 over the total sample size. So if you have 10 to the power 5 samples, then you want to make sure your delta is smaller than 10 to the power minus 5. In our case, we had 10 to the power 4 samples across all the data sets, so this works. Order of 10 to the power 4 samples, so this works. And why is epsilon 10? This 10 seems like it still seems insanely high. Uh, so like any method that gives you privacy, there's a privacy utility trade-off here. And we found that epsilon equals to 10 gives us sort of the best balance on that trade-off. And in practice, many machine learning models, such as let's say the Google Chrome, which also uses differential privacy, or the next word prediction on your keyboard, Android or Apple, which also might use differential privacy. These things often these days report 7, 8, 9, 10, 11, these kinds of epsilons. So naturally, for tasks where you need a much stronger notion of privacy for that particular client, this might not be enough. But what we observed in practice is differential privacy still sort of provides a North Star. So even for epsilons which are bigger than 1, the more you decrease your epsilons, we do see in practice that both our reconstruction and membership inference attack ability, they tend to decrease. So there's emerging theory about like how bigger epsilons can also give you a reasonable privacy. There's a whole cottage industry that goes into privacy accounting, which can actually show that your mechanism might actually have better privacy than you might think, and things of that nature. But for now, we're gonna stick to epsilon 10 and delta 10 to the power minus 5. Just to summarize again, like make the point that I said before, DP essentially is trying to protect against conclusion that strongly depend on an individual's record, which is why we are looking at things like L2 sensitivity. But it still doesn't prevent us from learning about the population. And that's the whole point here. We want the public distribution to not learn anything about a single chest X-ray, but still be able to learn some population level features about how X-rays in humans are generated. And a canonical example where actually DP type things were used, and actually some of the earliest local DP research happened in survey design and statistics communities, where people wanted to ask people about sensitive attributes, and DP provided. It was not called differential privacy back then, but the randomized response mechanism, for instance, it was used to actually control the sensitivity of a single patient. And of course, if you have differential privacy, then whether or not a single person says truly they smoke or not, you would still get like a reasonable estimate of cancer risk here. One very important caveat, the guarantee that I showed you on the previous slide is for the big public diffusion model. We still cannot release the local models. You might remember I put a lock sign on the local model because the hope is that the local model stays at the hospital. All of this does not still allow you to release the local model. In order to be able to release the local model, we would need to do something like differential private training of the local model on the client, which here we don't do. A client can also not release the synthetic data. So they cannot start selling the synthetic data while making sure that their own privacy would be intact, because all we've given them is like a privacy guarantee on the public model. We've not actually said that your own synthetic data would not leak information. So if they're doing things internally, this is fine. But the moment they actually start publishing things publicly, like inferences or things like that, you would need to do more careful privacy accounting or need to use DPSGD on the client in order to get something. But the silver lining is, if one client chooses to do this, if one client just defects and chooses to declare their model, then the other client who did not choose to do that still gets the privacy protection because the public model itself is protected. And differential privacy, if you've not seen this before, has this property called post-processing, which is that if a mechanism itself is differentially private, then if you pass it through any other algorithm F, uh, let's say that this is just deterministic right now, it still gets the same differential privacy guarantee. And thus, any deterministic post-processing of a differentially private output cannot leak any more information. And you, for randomized functions, for randomized post-processing, you can again extend this by looking at random protocols as distributions over deterministic ones. And this tells you that once you have like a privatized model, you can't do things like look at its weights or do multiple calls from it and somehow learn more about it. Like all the information statistically there is to know is capped by differential privacy. And just to give you a bit more perspective again, so a lot of this was developed as this progression of increasing privacy protection in surveys. And as a result, around 2010, the US Census actually started using differential privacy in everything it releases. And the context I was giving you before, this is this 1965 paper from Warner in JASA, which actually introduced the randomized response algorithm. And randomized response algorithm is actually one of the earliest algorithms which gives you local differential privacy while giving you reasonable guarantees about learning some estimate on the population. So yeah, I mentioned before, Apple uses these things, Google Chrome uses differential privacy, and there are other services which also use this. One more thing I actually want to say, take a step back and talk about is privacy is really a spectrum, and differential privacy falls somewhere on that spectrum. So on the very left, if you just do anonymization followed by some central storage and some centralized analysis, the kind of approach that we first saw, that would have some privacy. You might not be able to naively tell whose data it is, but what's still possible is that you can identify people by looking at either side information or by trying to look at things like how far are they from the average statistic or the median statistic. So for instance, like in US, it's well known that uh, a person's PIN code, date of birth, and I think gender uniquely reveal about 80% of the people. And even things like, and people can do things like cross-referencing multiple data sets. And one of the most controversial things that happened in 2010s was this was before census started using actually differential privacy. Someone actually mailed their senator a copy of their health records, and I believe this was a student doing some course in privacy or like security, and they actually looked at publicly available census data, publicly available health insurance data, and then were able to actually do this type of stuff. So anonymization doesn't do much. Then there was federated learning, which was super popular. I think it came around 2017. But federated learning, all it guarantees is that the raw data always stays on the client. It also still doesn't give you a formal privacy guarantee because the way we saw diffusion models could memorize data, other machine learning models, especially large over parameterized models, can also memorize data. So even though your raw data might not leave the device, the model itself, which is deployed and is public, might leak sensitive information. And you might have seen things like SQL injection attacks into large language models, which allow people to actually generate things from the model that are illegal or things that the model providers claim the model was not trained on. So federated learning by itself doesn't give you a very strong notion of privacy. There's the central differential privacy where we saw you have this trusted server and then the server can do the noise addition. And further down on the right is this local differential privacy notion, which we are able to provide in this paper. And there are actually orthogonal ways to talk about privacy. Like from federated learning, you could actually go to something which is becoming really popular these days, which is doing computations on a trusted compute environment where you actually have pre-decided on what types of computation you want to do on a particular data set. So you aggregate the server in a data centralized data server, and these pre-decided, pre-signed upon computations are the only computations that happen. So you know that an adversary, even with side information, cannot do some nasty attack on the model. And there's also, of course, cryptographic tools like multi-party computation, which can be used. Some of these techniques are, it's possible to combine them. Some of them can't as easily be combined, but yeah. So besides local differential privacy, there's one more aspect of diffusion models that's actually super useful to guaranteeing privacy, especially for medical imaging datasets. So for medical imaging datasets, you could imagine that some of the high frequency features or like finer features are the sensitive ones. So maybe as opposed to how like the basic structure of a chest X-ray would look like, the sensitive attribute is where is the tumor, what's the shape of the tumor, things like maybe turgidity of the tumor, and all those other things. So you could imagine there's almost like a fine features versus coarse features point of view, and finer features tend to be private. So that is actually useful because the way diffusion models work, they're actually doing this coarse to fine refinement of the image. And to give you an illustration here, on the bottom right of this image, you basically see the true data. The true data is actually four Gaussian mixtures. So it's a hierarchical Gaussian mixture model. So you have like four modes. Within each mode, you again have four modes. Within each mode, again, you have four modes, and so on. And you basically start on the top left from an isotropic Gaussian, because that's what the seed is. And then using a trained diffusion model, you progressively denoise things. And as you see in the first row, only the first level mode structure appears. In the second row, second level mode structure starts appearing. And finally, in the third row, the third hierarchy of the Gaussian mixture models also starts appearing. So you can imagine that diffusion models by design, even without any privacy noise addition, already have this coarse to fine refinement built into them, which is particularly useful for things like medical data sets where the fine features might be more sensitive. So this, all of this is nice, but I want to show you all of this also works. So let's look at membership inference attack first. So we tried this a lot, variety of data sets. So although I use this running example of chest X-rays, we are not at a point where it is possible to extend all of this to chest X-rays, because chest X-rays are very high resolution images in general. And the furthest we are able to actually extend this framework to right now is 256 cross 256 images. So you could actually get a lower resolution chest X-ray and indeed apply this protocol. But on interesting chest X-rays and CT scan images, we are still working on being able to extend some of these ideas to higher resolutions. So I'll not bore you through all the data sets. Let's look at the Celebi, which is the largest and most popular data set here. On the top, I'm again showing you membership inference attack numbers. So the area under the curve is 50%, which essentially tells you that it's pretty much like a random attack, or like no ability to attack here. And another useful metric is this true positive rate. So the true positive rate is my ability to predict that a point was indeed in the training data. So a true positive rate at 1% false positive rate is around 0.86. And the first thing is our model. And all of these are white box attacks. So white box attacks are ones which can actually do things like look at the weights of the model. They don't just get like a black box access to the model. They can actually look at the weights of the model. They can look at intermediate losses of the model and things of that nature to able to curate like a better attack. We didn't design a remarkably new attack method, but I'm just stating it's a white box attack. For non-private methods, so for methods for which you just don't think about privacy, what kind of numbers do you get? So for AUC, you get numbers. So S1, S2, S3, as you go from top to down, you're actually training the model more and more. So you start from about 61 AUC, you go all the way to 99.59. And if you want to look at true positive rate, as you keep training the model, you actually start seeing 93% true positive rate at 1% false positive, which is pretty high. So this is just a demonstration that Celebi indeed shows a very strong sort of affinity to membership inference attacks, and kind of like rehashing the same thing the Carlini et al. Paper previously talked about. But I said that in 2023, that paper tried to do differentially private training and failed. So what happens if you do DP training? Uh, Again, I'll not tell you immediately, but I have that number in one slide from now. But again, besides membership influence attack, what about reconstruction attack? So we also tried two different reconstruction attacks. So this is the noisy image in the first row. The second row is the clean image that noisy image corresponds to. So this is the noisy image uploaded by the client. So if you weren't already convinced that the noisy image doesn't look anything like the actual data, so this is like a visual proof of that. And the first attack we do is something which can access the global model as well as a denoiser which is trained on some other data set. So we have the client denoiser which is not public, but then the adversary might have some side information about the client and might be able to get access to a related kind of denoiser. So we use like a related denoiser. I'll not go into the details of what the related denoiser here is, but it doesn't really work. You can see the images that it generates. They look like faces, but they don't actually reconstruct the original image. Uh, and we also tried another attack, which does not have access to a denoiser. It just does something like a nearest neighbor type search, and it also fails. Both of these, by the way, were the attacks that were also used in the original Carlini et al. Paper in 2023. Besides privacy, so both of these were empirical sort of demonstrations that we have privacy. We also have like a utility guarantee. So we essentially try to learn like a mixture of Gaussians, and the mixture of Gaussians, you can imagine each mode is essentially something that corresponds to a class. And each client observes essentially its own mixture weights. So it sees samples from each class, but in variable numbers. And we basically apply our protocol, which is like a two-stage personalized federated diffusion model. And there's a shared denoiser and a local private and a local denoiser on the client. And I need to tell you what neural network we use. It's very hard to prove anything on complex neural networks. We use a very simple piecewise linear noise prediction architecture. More details are in the paper, and this is in no way saying this is a general guarantee for neural networks. This is a very simple stylized toy model. But essentially what you can show is that for class K, so QK is actually the original distribution on class K, and PMK is the distribution learned by our protocol for client M for class K. And when you look at the Wasserstein to distance, expected Wasserstein to distance, then you get the following guarantee. It depends, the first term depends on the total number of samples across clients for class K. And the second term depends on the number of samples on client M for class K. So you can imagine if there's a client that is deficient in a particular type of sample, it can still benefit from looking at samples from the other clients. And you can clearly see that as sigma goes to zero, this actually recovers the centralized rate where everyone just chooses to aggregate their data and train a single diffusion model. When sigma goes to infinity, this recovers like the local rate. So it's a mixture of both of those rates. And to see this in pictures like this is an illustration. Again, on the left, we have personalized training. So I'll tell you a bit what the data set is here. This is like a MNIST data set, 0 to 9 digits. But in order to produce some sort of data heterogeneity, we actually divided the data set into two classes. So there were minority classes. So the digits 2, 3, 4, 5, 8 appear rarely. And I believe the ratio was 100 is to 1, so 100 times less likely than the other digits, which is 0, 1, 6, 7, 9. And on the left is our model, on the right is pure local training. Pure local training is we just don't talk, we train on our data set non-collaboratively. And that is, of course, private because no one ever talked to each other. What we see is for our model, we have some weird images sometimes, but for the most part, we are actually able to generate good images for all the digits, both minority and majority digits. But for pure local training, it kind of collapses on the minority digit. It's not able to learn the structure very well, which is a demonstration that collaboration indeed helps. Because you could have asked me for the strawman, okay, a private baseline is to not collaborate at all. How well does it does? And this is a visual proof of that. And the previous slide was like some attempt to give some theoretical evidence like in a stylized model. And we repeat this analysis for colored MNIST for here we also change the foreground color. Again, I'll not go into the details of this one. a very similar experiment with syllabi dataset. Here, we actually control two attributes, gender and hair color, and actually try to do the following. We actually have four combinations of gender and hair color, and on each client, you only see three combinations, not the fourth one. And you have to learn the fourth one by learning the correlations across the two attributes. And I'll share my slides later, and you can see that the non-collaborative baseline actually doesn't do very well on the minority attribute again. Finally, I want to show you some quantitative evidence as to why our utility guarantee is actually good. So one way to look at whether you've actually generated images with good fidelity is to look at the images. The other way is to look at something called FID score. And the FID score is essentially some notion of divergence between the generated distribution and the original distribution in the embedding space. What's the embedding space? It's the inception model embedding space. Inception is one of the large models trained on ImageNet. So this is like some proxy to estimate the quality, and you can put a number on the quality of the images. It's not a perfect metric, but this is something vision community tends to use. And the lower the number, the better it is. So again, in the green box, you can see that the non-collaborative baseline, so the majority, minority, and average are basically the majority class, minority class, and the average class. So the overrepresented class, underrepresented class, and the average score. And we do improve for the majority class compared to the non-collaborative baseline, but more importantly, we improve drastically for the minority class. So if you have a rare patient sample, you improve for that. And I told you that there is at least one differentially private baseline now. So you can think of this as like a federated learning baseline where there's some differential privacy as well. And again, compared to this baseline at the same privacy level, we actually do better. Although the gain on the minority class is not drastic, here we do better on the majority class. So somehow adding privacy noise directly to the stochastic gradients does worse for the problem. And actually this gap, again, this is the gap between the non-collaborative baseline and the collaborative baseline as we increase parallelization of the number of clients, and the gap actually grows. We also have like a data infusion guarantee. So if you actually do downstream tasks with the data that we generate, then you can compare how well you do with the non-collaborative baseline synthetic data as well as our synthetic data. And again, we tend to do better. That's it. I want to leave you with a few future directions. So the first one I already mentioned. Why is it hard to extend all of these to the actual running example, which is X-rays and CT scans? You might have been feeling gaslighted because I showed you a running example, but later all the examples were over digits and faces. There were no X-rays. One issue is that clipping is, in our experience, it drastically deteriorates the X-rays and CT scans a lot more than it does like digits and faces. So the squinting argument where I told you that clipping partially noised images doesn't change how the image looks, that's not really true for these medical data sets. So we're trying to explore ideas where you actually do diffusion in a latent space. So you learn a neural network to actually project everything into another embedding space and then do diffusion in that space as opposed to raw images. And we have some promising advances there, but this is still going on. Another technique is to use like a separate local and global diffusion process. So if the diffusion process is essentially just a transportation map, you could have used a different one on the client and the server. Um, you could also use a much larger T naught, because if T naught is very large, not only do you get a strong privacy guarantee, but your sensitivity to clipping is also low. Another issue which we are exploring is medical data sets tend to have very localized sensitive information. So in a 1,000 x 1,000 X-ray image, only maybe perhaps the 100 x 100 bounding box around the tumor is sensitive. And that is the one which actually reveals more membership inference. So I have actually some numbers to show this is indeed true for colon cancer images with tumors. And I believe this is a generally true hypothesis across a variety of medical data sets, that there's this localized sensitivity. So with localized sensitivity, you could hope to do only diffusion in like some pixels with a lot more noise than everywhere else. So if you use a lot more noise in like a localized region, not everywhere else, you could hope that your process would be much more stable. And then finally, one problem, which is a general problem, which as far as I know, no one has a good answer to. diffusion models are not really good for learning the long tail of the distribution. And this is super important for applications like drug discovery, for astronomy, but I'm assuming also for electronic health record data where there are rare samples and you really want to be able to generate those rare samples. The whole reason perhaps you were doing this is you wanted a way to aggregate rare samples across the clients in like a differentially private manner. And I'm working on basically extending the very same ideas that I talked about today to also synthetic EHR data generation. And the way this works is you could either use Gaussian diffusion like we did today, or you could use some other types of diffusion like categorical diffusion, what are called like so-called discrete diffusion models to actually generate tabular, longitudinal or not EHR data. And pretty much the same idea can be extended, but there are, of course, more nuances that come in with the mixed data type that EHR data tends to have. And finally, I'd like to leave you with this takeaway. This is what really inspired me to write this paper, which is this observation and optimization that personalization, which is basically giving a client specific parameter in addition to like a public parameter, tends to improve privacy accuracy trade-offs in federated settings. And this idea of using personalization to sort of encode away the private information in one set of the model and then store the non-private information in something else is something which many people have used. And I'm pretty sure in other applications in biostatistics, which also care about privacy, personalization might be something you guys might be interested in. So that's all. Sorry for overshooting the time. And if you have more questions, I'm happy to answer.